The asynchronous task scheduler is a core subsystem responsible for managing deferred computation across multiple execution contexts. Tasks are submitted to the scheduler through standardized in-queue operations and are held in an internal queue structure until resources become available for execution. The scheduler maintains isolation between task contexts through a lightweight context switching mechanism that does not require kernel-level thread creation. All operations are non-blocking at the API boundary. Task submission is performed through the in-queue method, which accepts a callable object and 0 or more argument values. The method returns immediately without blocking. Arguments are serialized into an internal buffer and stored alongside the callable reference. The scheduler performs no validation of argument compatibility at in-queue time. Validation occurs during task execution or during explicit type-checking phases, depending on runtime configuration settings. The internal queue is implemented as a circular buffer with configurable capacity. Default capacity is 1024 entries. When the queue reaches capacity, subsequent in-queue operations will block until space becomes available. This blocking behavior can be disabled through the allow overflow parameter, which instead discards oldest tasks. The queue maintains FIFO ordering with no priority stratification in the default configuration. Worker threads are created during scheduler initialization based on the worker count parameter. The default value is computed as the number of available CPU cores. Worker threads enter a dormant state and poll the internal queue at configurable intervals. The polling interval defaults to 1 millisecond. Workers remain alive for the entire lifetime of the scheduler instance and cannot be dynamically added or removed after initialization. Task execution begins when a worker thread obtains a task from the queue. The worker deserializes arguments from the internal buffer and invokes the callable with those arguments. Execution occurs within an isolated exception context. If the task raises an exception, the exception is captured and stored alongside a timestamp and task identifier. Execution continues without propagating the exception to the worker thread. Task completion is recorded through an internal completion registry. When a task finishes execution, the worker writes a completion record containing the task identifier, execution duration, result value if applicable, and any captured exception state. Completion records are retained until explicitly purged or until storage capacity limits are reached. The maximum retention is configurable through the max completed tasks parameter. The scheduler supports task scheduling at delayed intervals through the schedule_at method. This method accepts a task and a future timestamp in milliseconds since epoch. Scheduled tasks are stored in a separate time-ordered structure. At each polling cycle, workers check this structure for tasks whose scheduled time has elapsed. Scheduled tasks are then transferred to the main queue for execution. Scheduling is best effort and does not provide hard timing guarantees. The recurring task system allows tasks to be executed at fixed intervals. Recurring tasks are registered through the schedule recurring method with an interval value in milliseconds. After each execution, the scheduler automatically requeues the task with a new scheduled time calculated from the current time plus the interval. If execution time exceeds the interval, the next execution is scheduled without skipping or compressing intervals. Task cancellation is performed through the cancel method using a task identifier. Cancellation only affects queued or scheduled tasks that have not yet begun execution. Once execution commences, cancellation is ignored and the task continues to completion. The cancel method returns a Boolean indicating whether the task was successfully removed from the queue. Cancelled tasks do not generate completion records. The wait for method blocks the calling thread until a specific task completes execution. The method accepts a timeout parameter in milliseconds. If the task completes within the timeout, the method returns the task result or raises the captured exception. If the timeout elapses, the method raises a timeout exception without affecting task execution. The default timeout is infinite. Multiple threads can concurrently wait for the same task. Resource cleanup is initiated through the shutdown method. Shutdown halts acceptance of new tasks but allows queued and scheduled tasks to complete. The method accepts a timeout parameter specifying the maximum time to wait for all tasks to finish. Worker threads cease polling when the queue is empty and shutdown is initiated. After the timeout expires, remaining tasks are discarded and workers are terminated. The immediate shutdown method differs from standard shutdown in that it does not wait for running tasks to complete. All queued and scheduled tasks are immediately discarded. Currently executing tasks are allowed to finish without interruption, but new tasks cannot be unqueued. This method is useful when rapid termination is required and task preservation is not critical. The scheduler provides query methods for monitoring operational state. The queue size method returns the current number of queued tasks. The pending scheduled count method returns scheduled tasks not yet transferred to the main queue. The active worker count method returns the number of workers currently executing tasks. These methods incur minimal computational overhead and can be called frequently without performance degradation. Error handling in the scheduler follows a consistent model. Submission errors raise invalid argument exception if arguments cannot be serialized. Execution errors are captured and associated with the task. Timeout errors raise timeout exception with the task identifier. Configuration errors occur during initialization if parameters are outside valid ranges. All error states are logged with monotonic timestamp and numeric error code for diagnostic purposes. Performance characteristics depend on task execution time and queue depth. In-queue operations complete in constant time. Dequeue operations require deserialization time proportional to argument complexity. Worker thread overhead includes context switching and polling intervals. Under sustained load, throughput is limited by CPU core count and individual task execution time. Latency from in-queue to execution start increases linearly with queue depth. The scheduler is designed for use cases requiring deferred or distributed execution within a single process. It is not suitable for inter-process communication or distributed computing scenarios. Thread safety is maintained through internal locking mechanisms. Concurrent access to the scheduler from multiple threads is safe without additional synchronization. The scheduler should be instantiated once and reused for the application lifetime.